Welcome to video 5, Decibel, the cascaded connection, logarithmic frequency scale, and the Bode plots. I will now take the laser pointer so that we can follow what I pointed. When we have the magnitude of a transfer function and we would like to turn it into a decibel scale, then we take the magnitude at a specific frequency, take the logarithmic value of it. Here the logarithmic scale of 10 must be used, and then time with 20. Then we have the transfer function value in dB. We can see it here on the transfer function magnitudes and the decibel equivalent. We have here the magnitudes. This is voltage over voltage, so it's a times. And we have it here in dB. If we look here carefully, we can see that 2 equals to 6 dB, a square root 2 equals to 3 dB, and times voltage over voltage, so V out over V in, is 1. Then we have 0 dB. If we have 1 over square root 2, we have minus 3 dB. So if we have 1 over the value, we get a sine inversion of this value. Equivalent, if we have 100 times, it's equivalent to 40 dB. If we have 1 over 100, then we have minus 40. Why do we need these magnitudes in dB? We see that here on the notch filter. It's a filter that's very good at filtering out one specific frequency. Here it's an American filter because it filters out 60 Hz. In Europe we would actually use 50 Hz. Sorry. We can see here the magnitude of the filter, and this is just V out over V in we have here. We have a linear scale down here. But if we turn to this part of the screen, we can see we have the transfer function magnitudes in the decibel equivalent, because we have 0 dB at 1. And then we go down in scale. They are not totally comparable because you can see the graph here is kind of large and here it's very dense. The idea to use the decibel scale is that you actually are able to see way more data on one small scale. Another thing you notice that is saying here passband. The filter let all these frequency pass, then one specific frequency stop, and then the other frequencies are passed again. The stop band is where we definitely want in the filter to have one frequency so low that we can regard it unimportant to the rest of the data we have. So here it wouldn't matter to get this value into our AD converter. Yeah, let's go further. If my mouse wants to. Now something about cascading transfer functions. We have one transfer function here that's cascaded with this transfer function. This could be two filters, one low pass filter and another low pass filter. We have to notice here we call V in equals to V in 1. So we know this is the V in of this transfer function, and we get a V out 1. So this is the output from transfer function 1. This output then becomes the input to the next transfer function. Vn2 that then goes into this transfer function and becomes transformed and then gives the output to then the overall block here output. We have already this equation about what is the transfer function. It is the complex output over the complex input. And for one individual, we can see for this one, we have Vout2 over the whole block becomes then Vout2 over Vin1. Because if I take the transfer function of the first block, h of 1, so this one, I have Vout over Vin1, and then I would have a transfer function here that says Vout2 over Vin2, but that's the same as Vout1. And then you can see this one cancel out and this one cancel out. So I actually get Vout1 over Vin1 and Vout2 over Vn2, and that's for each individual transfer function times each other. When we take it in decibels, we have it a bit more easy. Then we can take the decibel transfer function output and just add them together. That's a benefit because normally here we have to times them together. So let's look at what could it be. Here we have an example that the first transfer function is actually a low pass filter, and the second transfer function is also a low pass filter. When we have to find the transfer function, the first one, we have to notice that the second transfer function, this one, R2 and C2, is actually in parallel over C1. So when I want to find the transfer function of C1 in a cascade, I have to consider C1 is actually loaded with a series connection of R2 and C2. So we have to take that into consideration, that we actually have a loaded circuit. So when I find the transfer function 1, I have to consider that transfer function 2 is loading the transfer function 1. So let's go further to the next thing. When we have to plot transfer functions, we use the principle of 1 decade. That's a factor of 10. So what we show on a graph is from 10 to 100 and from 100 to 1000. That's the typical jumps. We can show some intermediate values. We could also use 1 octave. Perhaps some of you play a music instrument. Then you know 1 octave is a factor of 2. So a jump of 2 from 500 Hz to 1000 Hz, that would be a 1 octave, a jump in 2. In order to find out how many decades we have to sketch, we normally take the end frequency we are interested in showing and divide it by the starting frequency, and then take the logarithm of it. Then we get the number of decades we have to show. This is used mostly for filters, and beware, it's a logarithmic frequency scale. and for filter purposes this is the preferred one. So let's go to the next topic, Bode plots. A Bode plot is a plot of a decibel magnitude of a circuit's transfer function versus the frequency using a logarithmic scale. As you can see here on this small example, we have the break frequency. And at the break frequency, we know when it's first order filter, it has its specific characteristic. We normally sketch a filter at its break frequency, and since a first order filter will go down with minus 20 dB 10 times the break frequency, this is then very linear, easy to sketch with a ruler. So this is the typical response of a low pass filter, that we from the break frequency, 10 times the break frequency and 100 times the break frequency, know exactly at this point here we will have minus 20 dB, and at 100 times the break frequency we will have minus 40 dB because the slope is minus 20 dB per decade of this filter. So in a normal setting, when we have to design for a low pass filter, the Bode plot starts at 10 divided, the break frequency divided by 10. Then we have the break. So up to this point we draw with a ruler as a straight line. At the break frequency we have a direct slope of minus 20 dB per decade. So this is the magnitude sketch in dB. How will it look like for the phase? We will also like to show the phase. Remember that a low pass filter at the break frequency has minus 45 degrees. So this is a dot point where we sketch a point. Then we know when the phase actually starts changing at the frequency 10 times below the breakpoint frequency. So here we would draw a mark, and then up to this, from 0 degree to up to this mark, we draw a straight line, and from this mark until 10 times the break frequency, where we have 90 degrees phase shift, we draw a straight line through the point of 45. So this is then the sketch, and over 10 times the break frequency, it stays with 90 degrees phase shift. So this straight line approximation is the Bode plot. The actual phase of a low pass filter will have a way of smoothing around these points, and the maximum error we will actually get here is about 11 degrees, and in most cases also 11 degrees here. This is of no problem, because a sketch is telling us how should we design it. We know when we simulate it or when we measure it, it will have this actual curve, but for sketching purposes, we don't care. So how do we sketch it? If we want to sketch it more rightly, we have here the magnitude of the low pass filter. Perhaps you can see it. It's the standard equation we have used in the previous videos, and we also have the equation for the phase. So the first thing we do is to take the logarithm of the magnitude. also for the transfer function. So we do that by placing this equation inside the brackets here. And this is then the magnitude. Then we use that this equation here is on the log of 10. And then we use the mathematics from the logarithm. So the one up here becomes 20 log of 1. And then because we have a nominator, it becomes minus 20 log of the square root of what? That's the denominator. And then we know, or we can calculate that the logarithm of 1 actually becomes 0. So 20 times 0 is also 0. So we get minus 20 logarithm to what we have under the square. Then from math, we know that if we take the logarithm of a value that been rooted, we can take the root of and it becomes a half. So this square root we can actually replace by half. And then since we had minus 20 in the beginning, divide by half, then we get 10. So we have 1 plus f over fb, that's squared. Since this one plays so a little role when we act with the bigger values here, we can disregard it as approximation for frequencies that are way higher than the breakpoint frequency. So the 1 is left out, and then we can take this 2 out again using the principle of log to actually times it up with 20 again. So approximated Bode plot for a low-pass filter can then be drawn as f over fb, taking the logarithm into it and timing with minus 20. That would also sketch the Bode plot. For the phase, that's a bit different. We just have to remember that it's a straight line at 0 for frequencies below the breakpoint frequency divided by 10. And we get a sloping directly intersection with at the breakpoint frequency at minus 45. And then a horizontal line from 90 degrees to for frequencies that are higher than 10 times the breakpoint frequency. Oh, my mouse is working a bit strange. So let's see a small example. In this exercise 611, sketch the approximated straight line Bode, magnitude and phase plot to scale for the circuit shown in figure 6.17. So we have this circuit. It is a low pass filter. We can always test it by 0 frequency. Then this is an open circuit. And we have V in on V out. And for infinite frequency, the capacitor becomes a short circuit, and then we have 0 out because this is a short. So it is definitely a low pass filter. Next. So how do we do it? We have the transfer function for the circuit. It is the voltage divider equation. We beautify it so it says 1 plus j something here. So, and then we have 1 over plus JFOFB. We know the break frequency is 1 divided by 2 PRC, and putting in the values, we can calculate this is 1000 Hertz. So, for frequencies below 1000 Hertz, the Bode plot for the magnitude is a straight line up to the break frequency. And after the break frequency, it slopes down with 20 dB per decade. And the phase plot is also approximated by 0 below. Here should be, it's the break frequency divided by 10, so that's 100 Hertz. And above 10 times the break frequency, here we have 1000 Hertz, that's break frequency. So at 10 kilohertz, we have 90 degrees. But remember, at the break frequency, we have minus 45, so it goes through this point. So let's see the next slide. Here we have the graph, the sketch of it. This is the breakpoint frequency at 1000 Hertz. Above it, we have 0 dB, and we actually go at 10 times the break frequency, we have minus 20 dB. 100 times the break frequency, we have minus 40 dB. For the phase, one specific point for the low pass filter is minus 45. This is the phase we have at the break frequency. 10 times below the break frequency, that's the 100. It starts sloping, and before that it's 0. So we go a slope through this point down to 10 times the break frequency, and that's at 10 kilohertz, where it's 90, and from there on it slopes right away. So this is how we do Bode plot. Thank you for now.